We do the test on Monday.
Okay, g'day everyone. We'll get started. Max, is that your bag?
That is my bag, yes. Sorry.
Okay, so I've just painted up here a picture for the rest of the term. So this is where we are today, Monday, going through 3F. This is a skill where we're going to use our calculator a fair bit, so we're looking at some calculator techniques. On Wednesday we've got 3G, and that gives us Thursday. We're sort of starting to look at some test revision. And you can see Monday we're missing that lesson because it's a public holiday. Another revision lesson on that Wednesday. And then my proposal is to do the test here. Okay. Now, I'll run around and have a chat with people about it, but I don't think it's a good idea to do it next term. Okay, because over the holidays, I've actually got some homework I do want you to do over the holidays, some statistics, which is pretty easy, but so that's one of the reasons. The other reason is in the past, kids that have done it, they don't do any study in the holidays, they forget everything, they come back and they do badly, all right? If you're probably going to do best towards the end of this term. It's a tight timeline, but you've just got to put a week and a half into work, and hopefully that's where we're at, where we're good to go. Okay, so that's my plan. I'll talk to people individually about it. Excellent. Let's get started on 2F then. So we're talking about rates of change. So remember, my first few points are there, is if we have a function that f dash of x describes the slope of this function, or we can think of the slope as the instantaneous rate of change, right? That's how fast the function is changing for some value of x. So in our first example here, we have the height of a tree, right? The height of a tree is given by this equation. Then if this is the circumstance, h dash of t is going to tell you how fast the height of the tree is changing. So we expect the tree to grow, right? So initially it's going to be some seedling and it's going to get bigger. And so h dash of t is going to tell you how fast it's growing per unit of time. And we look here, we're given the height of a tree, t years. So our time is in t, and height is in meters. All right, I need to include that in the notes, but height's going to be in meters. Okay, so let's start. How tall is the tree initially? So that means we want to know how tall is the tree initially. We're talking about when time is 0. So we're saying, what's h of 0? So a couple of ways we can do that, right? We can put the number 0 in here. Okay, if we're going to do that, it's going to be 12 on top of 1 plus e to the 5. That doesn't really tell us much. It doesn't tell you how tall it is. We can put that in our calculator and evaluate it to 3 significant figures. Or we can graph the function, right? If we graph the function, so that's what I'm going to encourage you to do because we're going to be using our calculator here a bit. Pull your calculator out. Let's graph the function. I've already put it in there. Okay, 12 on top of 1 plus e to the power of 5 take x. And the v window I've got set, I'll just let you know the v window I've got for now is something like 0 to x to 20 and 0 to y to 12. Okay? So set your v window to that. We're talking about positive values of time, right? So we don't need to consider anything to the left of the y-axis. And so that's how I've generated this function. And what we want is when time is 0, we want to know what's the y value. So we can trace along it by pressing F1. And then if you type in any number, I want to know when time is 0, enter x value. What's the y value? 0.08. 0.0803. All right, so 0.0803 meters. We'll just keep it at 0.08. Meters. Could be 8 centimeters, right? Either of those will accept the answer. Generally, we answer in the unit that we've given it to us. All right, so another way I can get that, I don't just have to trace along it. Be familiar with these operations. In GSolve, we've got the y-intercept. That's going to be the y-intercept as well, isn't it? When x is 0, that's the y value. So that's our initial height. Okay, part B, after 6 years, find h of 6. This one I'm just going to get straight from my calculator. We're tracing along, and I'm going to go, what about when x is 6? All right, when x is 6, my y value is 8.772. 8.77 meters. B. Discuss as time approaches infinity. Discuss what happens to h of t as time approaches infinity. So we can look at the graph, right? We can observe the graph, okay? And you can see from your calculator, I'm going to use Desmos from now, is it's approaching some limiting value, all right? And one way you can determine what that is, I'll flick back to the calculator, is to just trace along it and use your arrow key and look at the y value. As I move across, y is getting closer and closer and closer and closer and closer to 12, but it's never going to reach it. It's going to be asymptotic to it. So we can say from looking at the graph that as t approaches infinity, h of t approaches 12. So the height of the tree is getting closer and closer to 12, but never quite reaching. That's its maximum height. Now I'm going to make a mathematical case as to why that's true. So I'm demonstrating to you, you can get that from the graph. This is worth 1 mark, right? You can get that from the graph. Here's how we can understand it's true. So let's think about this equation, right? And let's put a large number in. Let's put t is 1,000, all right? That's a large number. It's a large positive number. We can go larger if you want. But what you would have is you'd have 12, so h of 1,000 is going to be 12 on top of 1 plus e to the power of 5 take 1,000. All right, so we're putting 1,000 where the t is. And so what's that going to be? It's going to be 12 on top of 1 plus e to the power minus 995. Okay, now I'm just going to focus on this component. All right, I'm just going to focus on this component, e to the power of minus 995. What does that part mean? It means 1 on top of e to the power of 995, which is 1 on top of 2.72 times 2.72 times 2.72, 995 times. So we get this enormous number at the bottom. We have 1 divided by an enormous number, 1 divided by an enormous number. This whole thing is approaching 0. Okay, so this Already I'm anticipating in my mind, okay, we've got water leaking out of the tank, all right? Or if you consider the original function, it was decreasing. That means my derivative values are negative, right? So now I need to consider the part below the x-axis. So when I'm changing my V window, I'll just crank that down to -5 or something like that. -5 to 5. Shuffle it around until you can see, there it is, okay? I'll bring it up on Desmos so we can see it clearer. Get rid of that, get rid of that. Okay, so there's something I want to show you here. What is this function? This is the rate of change of the volume, all right? So it starts off at -2, and then it gets less and less and less and less and less. And that's what you would expect, right? If you have a tank and water's leaking out the tank, as the volume of water decreases, so does the rate at which it comes out, because there's less internal pressure pushing the water out. So the question asks us, when is water leaving the tank at the highest rate? Well, it's when time is 0. We don't have a local max or a local min here, but this is when it is most negative. All right? Every other value there, the rate is getting smaller and smaller and smaller. It's getting closer and closer to 0, right? So, to answer part F, when is water leaving at the fastest rate? When time is 0, initially. When time is 0, water is leaving at the fastest rate. It has the derivative is the most negative at this point. Excellent. Okay, so that's good. I'll just point out on the page, on the subsequent page, we have types of models, all right? So you're not required to know these, and in the past, it's never been something I've taught, all right? But you will see these pop up in the questions. So rather, you're required to know the calculus techniques. You're not required to know the properties of the different types of models and recognize them. But just in case you are interested, there they are. They're common types of models that pop up. So if we consider the examples we've talked about already, like this question we just did here was a logarithmic function, right? We have the volume changing, and then the first one we did was a logistic model. We had a maximum height that we should reach. So they've all got unique properties, but they're not part of the course for us to teach. Rather, they're something that does pop up a fair bit, and so you will, I put them there as a point of interest. Splendid. So let's have a go at exercise 2F.